Hello everyone, welcome to another awesome adventurous session on probability for AI and ML. I am your host Hassanul Banna Himel, currently studying in the Department of Computer Science in Brack University. Today is we will be hosting only one session on probability for AI and ML. I will try to cover as much as topic covering possible in today's session. So today is Saturday, 1st June. This session is supported by Global AI Bootcamp, Dev Changemakers, NSDC, and TensorFlow User Group Bangladesh. So, what are the only sessions topic or only probability sessions topic? In today's session, we will be learning about a brief history of probability theory. We will learn about what is probability theory. We will be I will be showing to you events and sample spaces, and finally we will conclude our today's session with multiple independent observations. So now let's jump to our today's session. So at first, let's see a brief history of probability theory. What is a probability? Probability is something like you will get this or you will get that. So it is happening from the ancient times. In the ancient times, early ideas of probability can be traced to gambling and games of chance in ancient civilization, such as Mesopotamia, Greece, and Rome. You can say like that you can gamble like today it will rain or today it won't be raining, like that. It is like possibility 50-50. Greek philosopher Aristotle discussed probabilistic reasoning in his works. In the 16th century, Girolamo Cardano, an Italian mathematician, Cardano wrote Libre de Ludo Alei, books on games of chance, or also we can call this probability, which included the first systematic treatment of probability. And if we look again in the 17th century, Blaise Pascal and Pierre de Fermat corresponded about problems related to gambling, laying the groundwork for probability theory. In the Also in the 17th century, Christian Huygens published De Ratiocinations in Ludo Allier. In 1657, the first book on probability theory, and it continues in the 18th century. Abraham de Moivre wrote The Doctrine of Chances in 1718, introducing the normal distribution as central limit theorem. We will learn something about limit theorem. And then later on the 18th century, Thomas Bayes developed Bayes' theorem, published posthumously in 1763 by Richard Price. And in the 19th century, there was more expanded version of the probability theorems. And in the 20th century, the Andrei Kolmogorov founded the modern axiomatic approach to probability theory with his 1933 work Grand Fabrique der or the foundations of the theory of probability. So we can say that in this early history and age, the mostly probability was based on like gambling or something like that. So, in the late 20th or in this current 21st century, probability theory continues to expand with applications in various fields such as statistics, quantum mechanics, finance, and machine learning. As we're in today's session, we're learning about machine learning or something like that. Our probability will be helpful to learn more about machine learning in development of computational methods and simulations such as Monte Carlo methods significantly advance this field. So we learned about the history of probability. So what is the probability theory? The definition is probability is a measure of the likelihood that a particular event will occur. It ranges from 0 to 1. We all know about the binary system, right? It is either 0 or 1. When it is 0, it is hello null, or it is none, or when it is 1, it is yes, or we can also say that it is working. So either it will be 0 or 1. So now let's learn the basic concepts. The sample space, the set of all possible outcomes of a random experiment. What is a event? A subset of the sample space, a specific outcome, or a set of outcomes. We will learn this in our next slides. And what is probability measure? A function that assigns a probability to each event in the sample space satisfying certain axioms. And what is the axioms of probability, or also the Kolmogorov's axioms? At first, it is non-negativity. For any event, the E or the P of E will be greater than 0, or it will be equal 0. It never will become any negative value, like from -1 to -infinity or something like that. And normalization, P of S is equal 1, where S is the sample space. And additivity, for any two mutually exclusive events, let's assume as E1 and E2, the P of E1 union E2 will be equal P of E1 plus P of E2. And what is random variables? A random variable is a function that assigns a real number to each outcome in the sample space. There are two main types. The first one is discrete random variables, and the second one is continuous random variable. So what is discrete random variable? Take one countable number of distinct value, it will be our discrete random variable, and the continuous random variable will be taken on an uncountable range of values. When we are doing something on a countable range, like let's assume I have a range from 1 to 1 million, I have a countable range, right? So it is a discrete random variable. And what is when we are doing something like I am having a value from, let's assume I don't know what is the value, so I don't know what is the range, so it will be our continuous random variables. What is probability distributions? Same here, we have something like discrete distribution and continuous distribution. In the discrete distribution, here we have examples that include the binomial, the Poisson, and the geometric distributions. And in the continuous distribution, here examples include the normal or the Gaussian exponential and uniform distribution. What is the law of large numbers? States that as the number of trials increases, the average of the result will converge to the expected value. This is also defined as the law of large numbers. Now let's see what is the central limit theorem. In the central limit theorem, it states that the sum or the average of a large number of independent, identically distributed random variables will be approximately normally distributed regardless of the original distribution. Now, what is sample spaces? If we look at in the definition of the sample spaces, the sample space of a random experiment is the set of all possible outcomes. It's denoted by S and includes every possible result that can occur in the experiment. Now, let's assume we have a coin. We have a coin. Each coin has two sides, right? each this one has heads and this one has tail. So when I will toss a coin one time, single coin toss, the sample space will be either it will be heads or it will be tails, right? It can be, I can surely say that this will come heads or this will come tails. This is always all about the probability. Also, it happens in the dice roll. When you roll a six-sided dice, the sample space will be from the 1 to 6. Either you will get 1 or 2 or 3 or 4 or 5 or 6. Like, you can get some random values each and every time. You can say like, this time I will get 6 or this time I will get 3 or something like that. You can't always predict what we will get. So again, when we are doing a coin toss twice, we will get 4 values. Like, we will get a head and head, we can get head and tail, we can get tail and head, and we can get a tail and tail. If I draw this one, like let's me draw this. It is not showing. Yeah, this one. Let's assume I have head, tail, head, tail. To connect each with everything, at first I will connect this head with this head. Again, this head with this tail. And same goes for this tail to this head. And finally, we can say this tail to this tail. So here what we are getting at first, it is head and then head and tail, and then for this one we will be getting tail and head, and finally we are getting tail and tail, something like this. We are getting 4 predicted values when we are tossing a coin twice. So what is events? The definition of an event is any subset of the sample space. An event can include one or more outcome. Like, if we look at the coin toss event again, you can either get heads or you either get tails. In a single coin toss, the event of getting a head is E will be equal heads, and it can become either it will heads and it will be tails. When we are dicing, we're rolling a dice, either if we want to get the even values. What are the values in a dice? Here let's assume I have a dice of in the variable d. Here it will be 1, 2, 3, 4, 5 and 6. So what will be the even values or what will be the odd values? When we're working with the even values, it will be giving us, let's assume we are working with even value, it will give us a subset of 2, 4 and 6. When you want to work with the odd values, we will be again getting another subset of 1, 3 and 5. And when we are tossing 2 coins, if you want to get a minimum of 1 head, what we have seen, we will be getting 4 values, right? It will be head and head, head and tail, tail and head, and finally tails and tails. So what is the probability of getting a head? You can get a head in the 3/4 time, or what is the probability of getting tail? It will be 3/4 what is the prediction of at least getting two heads, it will be one in a fourth, and same goes for the tails twice when you want to get tails twice. There are various types of events, such as a simple event, a compound event, a certain event, and a impossible event. So what is a simple event? An event that contains exactly one outcome, for example getting a 3 in a single dice roll, it is 3. So if you want to get a single value, like in a dice we have 6 numerical digits, or you can get 6 values, right? You can either get 1 to from 1 to 6, you can get any digit. From if you want to get a single value, like if you want to get a 4, the single dice roll here, it will be e will be our 3. Or when we are getting a head or tails, the probability of getting head will be in a single toss will be h. What is a compound event? In the previous slide, we have seen the more than one outcome. Here in this event, we will be getting more than one outcome. Like the prediction of getting 3 will be just one value. If you want to look at how we can find the even values, in this dice roll you can get 3 outcomes, right? It will can be 2, 4, or 6. Or if you want to get odd values, it can also become a 1, 3, and 5, something like that. Or now let's move on into our certain event, the event that contains all possible outcomes, like the entire sample space. For example, rolling in any number on a dice, like you can in this dice you can get any values, like from 1 to 6, it can be any values. And what is an impossible event? The event that contains no outcomes, it will be only the empty set. If you want to find 8 or 9 or 10 in a 6-sided dice, it can be, you can't never find something like after 6 you can get any values, from 7 to infinity you can get any values, so it will give you an empty set. There are some operations on events. It is the union, the intersection, and the mutually exclusive events. So what is an union sign? A union sign denotes as like this, and in the intersection sign it just put it down on the backside. In the union, the event that occurs if either event A or event B or both occur. Like if you want, let's assume we have a value in the A set 1 and 2, and in the B set we are getting 2 and 3. When we are doing A union B, we will be getting each and every single value from A and B. We will be getting 1, 2, and 3. So in this operation on events, we will be getting each and every numerical digits available in these sets. Like if you want, let's assume we have an A, B, and C. In the A we have 1, 2, 3, 4. In the B we have 2, 3, 5, 6, and in the C we have, let's assume 7, 2, 3. So here we are getting 1, 2, 3, 4, 5, 6, 7. So what will be in our A union B union C? Here we will be having 1 comma 2 comma 3 comma 4 comma 5 comma 6 comma 7. So this is our union. And what is our intersection? the event that occurs if both event A and event occur. Like same goes for, let's assume our this event. Here we have a set of again A, B and C. Here what are the common values? Here 2 and 3, 2 and 3, 2 and 3. These are common values, right? So if I want to A intersect B intersect C, when we do this we will be getting two values. It will be just 2 and 3. And finally, mutually exclusive events. Two events are mutually exclusive if they cannot both occur at the same time. For example, in a single coin toss, the events heads and tails are mutually exclusive. As I said earlier, you can't get both of them. Like you can get heads or you can get tails in the single event. Now let's move to our next slide. What is multiple independent observations? What is independence? Two events A and B are independent if the occurrence of A does not affect the occurrence of B. Mathematically, A and B are independent if P of A intersect B will be P of A multiplied by P of B. And what is multiple independent trials? When an experiment is repeated multiple times and each repetition is independent of the others, the outcomes form a sequence of independent events. Like example, flipping a fair coin 10 times where each flip is independent of the others. Like if you want to get each time you will be getting another every single different values. Like you can say in the next flip I will be getting a heads or tails, something like that. You can predict what is the future outcome will be. And what is the probability of combined events? Joint probability for independent events, like from the A1 to A to AN. Here n is any numerical values. N can be any values like from 500 or 10,000. N can be anything. The joint probability is given by P of, in the function area we will be getting A1 to AN. Here same as we have seen earlier, if I have P and let's assume Q, when we're no not this one, when I have A and B, if I am doing this P of A intersect B, here we will be getting P of A multiplied by P of B, right? So same goes for this one. When we are doing for from A1 to AN, we will be multiplying each and every probability of combined events will be each and every values multiplication. Now let's see in the examples. In the coin toss example, when we are doing a single toss, the sample space can be head and tails, and that is it. When we are doing two independent tosses, the sample space can be head and head, head and tail, tail and head, and tail and tail. The probability of getting heads in both tosses is 1/4. Like in the first toss it will be half, and on the second toss it will be half. So when we are doing like the previous, when we seen in this slide, the combined events, the probability, it will be become 1/4. And in the rolling dice, in the single roll the sample space will be 1 2 3 4 5 6, and in the two independent rolls we will be getting two of them. So the probability of rolling two sixes, when we want to get two six, it will become too much hard for getting two six in a same row. So the probability will be 1 of 36. Now let's learn about the law of large numbers. So what is our statement, or what is the law of large number? What was the statement given? So as the number of independent trials increases, the sample average of the outcomes will converge the expected value. So what are the example? If you want to flip a fair coin 1000 times, the proportion of heads will approach 0.5 as the number of flips increases. And that was our the law of large numbers. And now move to our central limit theorem. So what is the central limit theorem? What is stated, or what is the statement? For a large number of independent, identically distributed random variables, the sum or average will be approximately normally distributed regardless of the original distribution. So what is the example here? Rolling a dice for 100 times, that taking the sum of the outcomes, the sum will approximately follow a normal distribution if the number of rolls is sufficiently large. And finally, what are the applications we're currently doing with these things? With this, we're currently doing the quality control, testing multiple products from a production line to estimate the defect rate. We can find the defect rate, and we can find the definite estimation what will be the defect rate in the production line. We can also do the polls and surveys, conducting multiple independent surveys to gauge a public opinion. Like, let's assume we are doing a survey on a large university students. Let's assume I am doing a survey on what is the predicted results, or what is the average CGPA, or the result of a student of university students. We will be doing this survey on from the students from first year to fourth year. So here I will be picking, let's assume 20 students from each year. So what will be my picking list? We won't be picking the first benchers. Like, I can pick someone like who has a CGPA of 3.9 or 3.93 or something like that. And I also can pick someone who have a CGPA of 2.5 or 2.3. I can pick them, but in this whole 20 I can't pick all of them, like all of them will be these first benchers, or all of them are doing these results, something like that. I can't pick someone. I will pick randomly. I will pick someone who is moderate results, who are getting moderate results. So we can predict the, through this survey we can get what will be our minimal, or what will be the sum value. Also in the insurance, we're doing this one, assessing risk by analyzing a large number of independent claims. So that was it for our probability station. Hope that you all learned things in our probability station. So we are, as in this probability topic there is not much more topics will be covered. So only this one session will be conducted on the probability for AI and ML. This is your host Hasanul Bandai Himal saying goodbye to you guys. Thank you everyone.